When you first start your NDT journey, most of your theory training happens up front. But by the time you log all your on-the-job training hours and you're finally eligible to take the exam, that classroom knowledge isn't always fresh anymore. That's where the Liquid Penetrant Test Prep app comes in. With this app, you can keep your theory sharp while you build hands-on experience. It features two learning modes. Study mode gives you instant feedback and clear explanations for every question, helping you understand why each answer is correct. Test mode recreates the pressure of the real exam so you can strengthen your focus, speed, and confidence. Study anywhere, on breaks, in the field, or at home. The app tracks your performance automatically, showing you exactly where to focus next, so every minute of study moves you forward. Download the Liquid Penetrant Test Prep app today on the Apple App Store and take the next step toward a safer, stronger career in non-destructive testing.
Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger non-destructive testing programs. You can learn more about their services at the link in the video description. Welcome to the Deep Dive. Our mission today is to give you a shortcut to expertise in what's really one of the most foundational and critical methods in quality assurance: liquid penetrant testing crack detection. This isn't just, a basic check. It's a highly sensitive, non-destructive test, NDT, specifically designed to find those tiny surface-breaking flaws, the kind that could lead to really catastrophic failures if missed.
And foundational is definitely the right word. I mean, the basic idea is, well, it's ancient, really. Long before we had the sophisticated dyes and chemicals of today, the core concept existed as the oil and whiting technique. Yeah, think about those huge, heavy steel parts back in the day, like axles for early railroad equipment. Really critical stuff.
All right, I can picture that. Massive steel parts. How do they check for tiny cracks back then without modern tech like X-rays?
Well, what they do is dunk the whole component into heavy, often dirty crankcase oil.
Okay.
That oil would naturally seep into any cracks open to the surface. Then they'd wipe the surface clean, or clean-ish, and coat the whole thing with powdered chalk. Whiting, they called it.
Hence the name.
Exactly. And the oil trapped inside the crack would then slowly be drawn out, absorbed by the chalk, creating a visible stain, an indication. That simple action, that bleed out, is precisely the principle we still rely on today.
So we basically swapped out the dirty oil and chalk for much more advanced chemistry, but the underlying physics, the engine driving it, is identical.
Pretty much, yeah.
So our goal here is to really unpack the science, that bleed-out mechanism, capillarity, right? And then walk through the very precise steps you need to follow. Because it sounds like if you mess up even one step...
Oh, absolutely. The entire test can be invalidated. That procedural discipline is everything. The whole test hinges on capillary action.
Right.
That's the phenomenon where liquid moves, often rises, within a narrow space. It's driven by this competition between two forces. Adhesion, that's the liquid sticking to the solid surface, pulling it into the crack, and cohesion, which is the liquid molecules sticking to each other.
Okay.
For the penetrant to work effectively, adhesion needs to win out. That allows the liquid to basically climb into that tiny void, that discontinuity.
So if capillary action is the engine, you mentioned dwell time earlier, this time the penetrant sits on the surface. Is that like the throttle? How much does that vary?
It varies a lot, and yeah, that's our first major control point. The dwell time needed depends completely on the material being tested and the kind of flaw you're looking for.
Okay.
You see, penetrant gets into wide openings pretty fast, but for those really narrow, tight flaws, like fatigue cracks maybe, you might need 2 to 5 times longer for the penetrant to fully soak in compared to a wider flaw.
Wow, that's a big difference.
It is. So, for example, checking common aluminum or magnesium alloys might need, say, 15 to 30 minutes. But if you're inspecting critical stainless steel welds or forgings, that time jumps significantly. You might be looking at 30 to 60 minutes easily.
So the part itself really dictates the process, doesn't it? Not just what the technician feels like doing.
Exactly.
Okay, before we dive into the actual steps, maybe we should quickly cover the key terms, the language the industry uses for these things.
Good idea. There are 3 really crucial terms in NDT. First, a discontinuity. That's just any break or interruption in the normal physical structure. Could be a scratch, an area where weld didn't fuse properly, a gas pocket.
Got it, just an interruption.
Right. Then you have an indication. That's the visual sign, the image that shows up after the test that tells you a discontinuity is present. It's what the technician actually sees.
Okay, the visual clue.
And finally, there's a defect or a flaw. Now, this is a discontinuity that's serious enough, based on the engineering standards or codes, to make the part unusable, unserviceable. Very important point. Not every indication means it's a defect.
Right, but every indication points to something that needs looking at.
Precisely. It flags a discontinuity that has to be evaluated.
Okay, let's get into the process then. Step 1, pre-cleaning and drying. I've heard people say this is the most critical part. Like, if you fail here, it's game over for the test.
That is absolutely 100% correct. If that discontinuity is blocked by anything, could be oil, dirt, scale, even just moisture or residue from cleaning chemicals, the penetrant simply cannot get in.
Adhesion fails.
Adhesion fails, capillary action can't happen, the test is useless. Honestly, inadequate pre-cleaning, that's probably the #1 cause of false negatives, missing real flaws out in the field.
And there's a flip side too, isn't there? A danger in trying to clean too aggressively, especially with mechanical methods?
Oh, definitely. Big hazard. Using things like grinders, abrasive blasting, or even peening can inadvertently smear the metal surface. Or it can cold work it.
Smear it.
Yeah, it basically pushes or flows the surface metal, physically closing off the opening of an existing crack or discontinuity.
Yeah.
If that smeared layer is there, the penetrant can't get in, and you'll completely miss the flaw.
That's a huge risk. You could sign off on a bad part just because you cleaned it the wrong way.
It happens. And if that surface gets smeared, sometimes the only fix is to use chemical removal, like etching or pickling, just to get rid of that damaged layer and make the test reliable again.
Wow. Okay, so assuming we've cleaned correctly and the part is dry, we move to step 2, penetrant application and dwell.
Right. The main goal here is just getting a nice uniform film covering the entire surface you need to inspect. Make sure it's thoroughly wetted.
And you mentioned dwell time variations earlier.
Yes, and related to that, there's a technique called drain dwell, which is often recommended. It's more economical, uses less penetrant, but it also improves performance.
This is to do that.
As the part sits and drains, the lighter, more volatile solvents in the penetrant start to evaporate off the surface. This actually increases the concentration of the dye in the penetrant that is trapped down in the flaw.
So it makes the eventual indication potentially brighter, more intense.
Exactly. You get a stronger signal when it bleeds back out later.
Okay, makes sense. Now, step 3, excess penetrant removal. This sounds like where the real finesse comes in. You need to get rid of the surface stuff without pulling out what's inside the flaw.
This is where the sensitivity of the test is really controlled. It can be tricky. We basically have 3 main ways to do this.
Yeah.
Method A uses water-washable penetrants.
Okay.
These are pretty economical because the emulsifier, the stuff that makes it washable, is already built into the penetrant formula. The downside is the penetrant in the flaw is also emulsifiable. So if you overwash...
You got to out of the crack.
Precisely. So you have very strict controls. Water pressure can't exceed 50 psi. That's like gentle garden hose pressure. Definitely not a pressure washer. And the water temperature needs to be controlled too, usually between 50 and 100 degrees Fahrenheit.
Careful control to protect that trapped penetrant. What if you're out in the field, maybe doing a portable inspection?
Then you'd likely use solvent removable, which is method C. And the absolute rule here is you apply the solvent only by wiping with a clean, lint-free cloth that's dampened with the solvent.
Dampened, not soaked.
Right. You never flush the surface with liquid solvent. That would just dissolve and wash away everything, including the penetrant and the flaw. Strictly prohibited.
Gotcha. Wiping only. And the third method, you said often higher sensitivity, but more control needed.
Right. Those are the post-emulsifiable methods. Here, the penetrant itself isn't washable. You apply it, let it dwell, remove the gross excess maybe, and then you apply a separate emulsifier agent.
Okay. An extra step.
An extra step, but it gives you more control. Method D, which uses a hydrophilic or water-based emulsifier, is generally considered the most sensitive. It usually involves a quick pre-rinse with water first to get most of the surface penetrant off before applying the emulsifier.
Like pre-washing a greasy pan.
Kind of, yeah. It makes the emulsifier's job easier and more controlled. But, and this is critical, you have to control the emulsifier dwell time very carefully. Leave it on too long, and it can actually start to diffuse down into the flaw and emulsify the penetrant you wanted to keep.
Oh, so it can undermine the test from the inside out.
It can completely remove your indication before you even get to see it. So yeah, mastering that removal step, whichever method you use, that's really a key part of the art of liquid penetrant testing. We'll take a quick break, and when we come back, we'll talk about the developer, how we finally make that hidden flaw visible.
We'd also like to recognize Skaggs Media LLC as the creative force behind today's podcast. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. Find out more at skaggsmedia.com. All right, welcome back. We've navigated the critical steps: perfect cleaning, proper penetrant application and dwell, and that very careful excess removal. Now we're at step 4, development. This is the payoff, right? Making the invisible visible.
This is the moment of truth, yeah. The developer is usually some kind of fine powder, maybe applied dry or suspended in a liquid carrier, and it does 2 key things.
Okay.
First, it acts like a blotter. It uses capillary action again, but in reverse, to draw that trapped penetrant back out of the discontinuity onto the surface. This is the bleed out we talked about earlier.
We're folding the evidence out.
Exactly. And second, as it does that, it spreads the indication out a bit on the surface, making it larger and easier to see, and it provides a high contrast background, usually white.
So the tiny line of the crack becomes a slightly wider, more visible line on the white developer background.
Precisely. Amplifies the signal.
Is there a type of developer that's known for giving the sharpest, most sensitive results?
Generally, the non-aqueous wet developer, that's a powder suspended in a volatile solvent carrier, is often cited as the most sensitive. Part of the reason is that the solvent itself can kind of help dissolve and pull the penetrant out, assisting that bleed out action.
Okay.
But there's a really important note for any wet developers, whether they're water-based or solvent-based.
Yeah.
The developing action, the bleed out, doesn't really kick off until all the liquid carrier, the water, or the solvent has completely evaporated and the surface is dry.
Oh, interesting. So you apply it wet, but it only works once it's dry.
That's right. And there's another timing issue here, too. Development time is also critical.
How so? Can you leave it on too long?
You absolutely can. If you let it overdevelop, leave it on way past the recommended time, the indication will start to degrade. It'll spread out too much, become fuzzy, indistinct, just a smear or a blotch.
So you lose the definition. You can't tell what it is anymore.
Exactly. You can't interpret it properly. It's this window. You need enough time for the bleed out to form clearly, but not so long that it diffuses and loses its shape. Another critical timing element.
Right. It seems like timing is everything in this process.
Yeah.
Okay, let's talk about actually seeing the indication. Visible dye versus fluorescent. Why is fluorescent often seen as the sort of gold standard for sensitivity?
Well, fluorescent penetrant testing, that's type I, it's generally more sensitive, mainly because of contrast. That bright, glowing, yellow-green indication under black light just stands out so dramatically against a very dark background.
Much easier to spot than, say, a red line on a white background.
Yeah, the human eye is just much better at picking up that luminous signal in the dark. The contrast ratio is significantly higher, especially for really fine, tight cracks.
And achieving that high contrast means you need pretty specific viewing conditions, right?
Oh, absolutely. You must view it under black light, which is technically UVA radiation. And the inspection booths have strict requirements. You need a minimum UVA intensity hitting the part, typically 1,000 microwatts per square centimeter.
That sounds like a lot.
It's a good amount of UV, yeah. And at the same time, the ambient white light in the booth has to be kept really low, no more than 2-foot candles. It's very dim, like twilight.
To maximize the contrast.
Exactly. And just as important, the inspector needs to let their eyes adapt to that darkness for at least 5 minutes before they even start looking. Just like walking into a dark movie theater from bright sunlight, you need that adaptation time to reach peak visual sensitivity.
Makes sense. Now, we've already established the big limitation. Liquid penetrant testing only finds flaws that are open to the surface. Are there other limitations maybe related to the shape or geometry of the flaw?
Yes, there are. Remember how capillary action works best in tight, narrow spaces?
Right.
Well, if you have a discontinuity that's very wide but also very shallow, think like, the width is much greater than the depth that might get missed.
Why is that?
Because that wide, shallow opening doesn't create a very strong capillary pull, and it doesn't hold much penetrant. What little penetrant does get in might evaporate too quickly, or it might just get washed away too easily during the removal step. There's not enough reservoir to create a strong bleed out.
Okay, so wide and shallow can be problematic. Let's shift to interpretation. The technician sees an indication. How do they figure out what kind of flaw it actually is? Does the shape give clues?
Absolutely. The morphology, the shape, and appearance of the indication is key. For instance, cracks almost always appear as thin, linear lines.
Makes sense.
And you can sometimes get a hint about the depth, too. A deeper crack holds more penetrant, so the bleed out might be a bit wider or maybe brighter and more intense.
Okay.
Now, very tight cracks, like maybe new fatigue cracks, sometimes they don't form a solid line right away. They might appear as a series of very small, distinct dots, but lined up in a continuous formation, still linear, just dotted.
Interesting. What about flaws that aren't cracks, like holes or something?
Right, like porosity. Those are usually small gas pockets trapped in the metal. They typically show up as multiple rounded spots, maybe scattered across an area, pretty distinct from a line.
Okay. Round spots.
And then there's something called microshrinkage, which you often find in castings. This tends to look different again. Often it produces sort of pale, fuzzy, diffuse blotches, less defined than porosity spots because the flaw itself is often like a little network just under the surface, so the bleed out is slower and spreads out more.
So the look of the indication really tells a story, which brings us to a really crucial point. Who gets to make the call? Who decides if that indication means the part is bad? We need to be clear about interpretation versus evaluation.
Yes, that distinction is vital. Interpretation is the process of figuring out what type of discontinuity likely caused the indication you're seeing. Is it a crack? Is it porosity? Is it just a surface scratch?
Identifying the cause.
Right. Evaluation, on the other hand, is the process of deciding whether that specific discontinuity, now that you've interpreted it, is acceptable or unacceptable according to the specific engineering drawings, codes, or specifications for that part.
Okay. And who has the authority to do that evaluation?
This is a really critical point for industry understanding. Personnel who are qualified and certified to Level 2 or Level 3 in liquid penetrant testing are trained and authorized to perform both the interpretation and the evaluation independently.
Independently. So they don't need an engineer or a supervisor to sign off.
Correct. Based on the approved acceptance criteria for that specific job, a certified Level 2 or Level 3 technician makes the final determination of whether a discontinuity is severe enough to be classified as a rejectable defect. That responsibility lies with them.
That's a significant level of responsibility. And it underlines why the process control, the chemicals used, everything has to be spot on. Which brings up one more potential issue, a kind of hidden danger with the chemistry itself. Trace elements.
Oh, yes. This is a major concern, especially when testing certain types of materials. We're talking about high-temperature alloys, things like nickel-based superalloys, titanium, some austenitic stainless steels.
Used in aerospace, power generation,
Yeah,
critical stuff.
exactly. These materials can be very susceptible to something called stress corrosion cracking. And it turns out that if even tiny trace amounts of certain elements, specifically sulfur or halogens like chlorides and fluorides, are left behind in a crack or crevice after the penetrant test.
Oh.
Yeah, when that part goes into service, especially at high temperatures, those residual elements can initiate or accelerate corrosion and cracking. It's like leaving a tiny chemical attacker behind.
So the test itself could inadvertently cause a future failure mode.
Potentially, yes, if the wrong chemistry is used. That's why, for these critical applications, it's mandatory to use special low-sulfur and low-halogen penetrant materials where the levels of these harmful elements are strictly controlled to near zero.
Wow. Another layer of control needed based on the material. So if we kind of synthesize all this, looking back at our mission, understanding liquid penetrant testing really comes down to mastering this whole chain of controlled variables, doesn't it?
It really does.
From the pre-cleaning method to the alloy dictating the dwell time, the geometry influencing the removal technique, the sensitivity needed maybe pushing you to fluorescent and controlled lighting, and even the service temperature demanding specific chemical purity.
That sums it up perfectly. The reliability of the entire test depends on controlling every single one of those factors. You're harnessing a simple natural force capillary action, but you need that meticulous step-by-step procedural adherence to make sure it reliably finds flaws in parts under incredible stress, like turbine blades or nuclear reactor components.
It's really quite something that the safety of some of our most advanced, complex technology still relies fundamentally on the same physical principle that someone observed using dirty oil and chalk, probably centuries ago.
It is a fascinating link, really. Ancient observation enabling modern safety and integrity.
A truly timeless technique. Before we wrap up, just a quick reminder that AMS Level 3 is here to support your non-destructive testing needs, whether it's Level 3 consulting, training and mentorship, or compliance solutions like NADCAP and FAA readiness. To learn more, visit amsl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.